The properties, preparation, and reactions of carboxylic acids will be described in this video, as well as the preparation of nitriles and their reactions with hydride reducing agents and organometallic reagents. The hydrolysis of nitriles to carboxylic acids will be included in the notes for the next chapter. The carboxylic acid functional group is called a carboxyl group, and it contains both carbonyl and hydroxyl functionality. Carboxylic acids are found in a number of important naturally occurring molecules, including amino acids and fatty acids, and because of the hydrogen bond accepting ability of the carbonyl and the hydrogen bond donating ability of the hydroxyl, they form dimers in solution, which makes them fairly high boiling. The OH bond of carboxylic acids is much more acidic, much more labile, much more easily dissociated than the OH bond in molecules like alcohols or water, as demonstrated by the big difference in pKa. So why is it so acidic? Why are carboxylic acids so acidic? Because when you take the proton off of an alcohol molecule or a water molecule, you end up with a localized anion on oxygen, only one resonance structure. But if you take the proton off of a carboxylic acid, you end up with a resonance stabilized anion. The acidity of carboxylic acids can be increased by placing electron withdrawing groups on the carbon next door to the carboxyl group. Through an inductive effect, they withdraw electron density and they'll stabilize the minus charge that's generated upon removing a proton from a carboxylic acid. How can a molecule that is an acid by nature can also be basic? Well, the carboxyl group will not dissociate into OH-, so it's not a source of OH-. It can be basic in the sense of Lewis basicity. It's possible for either of the oxygens of the carboxyl group to be protonated by an acid, such as H+. However, only one oxygen will be protonated. Why is that? Well, if we protonate the carbonyl, you end up with a structure that looks like this. If you protonate the hydroxyl of a carboxylic acid by path B, you end up forming a species that looks like this. Take a look at the positive charges. In the lower species, the positive charge is localized. There's only one resonance structure for this molecule, but in the upper molecule, where the carbonyl is protonated, it's possible for the other oxygen to take on some of the positive charge, as demonstrated by drawing this other resonance structure. So you have two resonance structures, that is a more delocalized positive charge, and you know that the more delocalized the charge, or radical, in this case a positive charge, the more stable that charge is and the easier it is to form. So this is the only pathway that occurs. Therefore, in your mechanisms, when you encounter molecules that have a carbonyl group attached to an oxygen or a nitrogen, when you protonate that molecule, you're always going to be protonating the carbonyl because you're going to end up with a more stable positive charge. How do you make carboxylic acids? How do you synthesize carboxylic acids? From what other functional groups can carboxylic acids be made? You've already encountered up to this point three methods to make carboxylic acids, one of which is shown at the bottom of the page. You can make an arene carboxylic acid by the oxidation method shown here, but that's only to make arene carboxylic acids. Our synthetic target will be propanoic acid, shown here, and we'll synthesize that by four different ways. You know that you can make a carboxylic acid by Jones oxidation of a functional group that has carbon in a lower oxidation state. In this case, it would be 1-propanol, or it could even have been oxidized, or I should say synthesized by the oxidation of the aldehyde propanal. So either of these could be oxidized with Jones reagent to give you propanoic acid. You know that ozonolysis of triple bonds will give you a carboxylic acid. Remember, in ozonolysis, for every bond to another carbon in the triple bond, in the product you will end up with a bond to oxygen. So this carbon has 3 bonds to the other carbon, and in the product it has 3 bonds to oxygen, 2 to the carbonyl and 1 to the OH group. One that you haven't encountered before, but you have encountered a similar type of reaction, is the reaction of a Grignard reagent with a carbonyl species to give you this carboxylic acid salt. Remember, when you do retrosynthetic analysis on a product that's made by a Grignard reaction, you identify the bond that's being made, and you recognize that the portion that contains the oxygen must have come from the carbonyl species, and the other portion came from the Grignard reagent. So what's going to be the carbonyl species? If this is a single bond CO, that must have come from a C double bond O, which means that if you took a Grignard reagent and you treated it with solid CO2, which is dry ice, you'd make the new carbon-carbon bond, making this carboxylic acid salt, and then you just protonate the oxygen and you make the carboxylic acid. So this is one way to make a carboxylic acid, by a carbon-carbon bond forming reaction. Another way to make a carboxylic acid by a carbon-carbon bond forming reaction is by making a nitrile from an alkyl halide, and you know how to do that. That's basically just an SN2 reaction with cyanide as the nucleophile, displacing a leaving group, halide or tosylate. You get a nitrile, and notice that nitriles, C triple bond N, you have carbon bound 3 times to an atom more electronegative than itself. They can be converted to carboxylic acids by hydrolysis. This carbon is in the same oxidation state as the carboxylic acid carbon. Carbon bound 3 times to nitrogen. Here we have carbon bound 3 times to oxygen. So we can consider them to be in the same oxidation state. This is not an oxidation reaction. This is just hydrolysis. We will go through the mechanism, step-by-step mechanism, in the video that covers the chemistry for the next chapter. So here you have 5 ways to make carboxylic acids. Let's put 4 of those 5 ways to make carboxylic acids to use in solving this problem, where we have to synthesize this carboxylic acid from cyclohexanone. When you start a synthetic problem, you have a tendency or an urge to write out the starting material with an arrow and then try to work forward from there. But there are so many different things you can do to cyclohexanone. You can go in an infinite number of directions. Rather than do that, have a more directed approach and apply the systematic way to approach synthesis problems that I described earlier. Question number 1 was, what's the functional group in the molecule you're synthesizing? It's a carboxylic acid. The next question is, do I know any carbon-carbon bond forming reactions that make carboxylic acids? And the answer is yes. Let's look at all of the ways that you know to make a carboxylic acid, just to make this a complete retrosynthetic analysis. We just described 4 different ways. We said that it's possible to oxidize this alcohol to a carboxylic acid with Jones reagent. We said that we could hydrolyze with H plus and H2O this nitrile and get this carboxylic acid. And this is a carbon-carbon bond forming reaction where you can make a carboxylic acid in the very last step in the synthesis. You can also ozonolyze an alkyne. So that's how retrosynthetic analysis works. You look at the target molecule and then you look at the very last step and say, where does this come from? And this might help you direct your synthesis, because at some point, if you go back maybe another step, you'll be able to look at the starting material and say, oh, I know how to go forward from there. That's the way to do it. You don't have to go back completely. Just go back to a point where you know how to go forward. Now let's analyze the 4 different routes. In retrosynthetic analysis, you come up with these branches in your retrosynthesis tree, and then you prune the branches. Some of these may not be very good. Like, for example, let's take a look at this bottom example here. We know that it is possible to ozonolize this triple bond to get this carboxylic acid. There's no doubt about that. But then the next question is, this is my new target now. I'm going to focus on how do I make this, because if I had this, I could easily convert it to this. And now I focus all my attention on this. Do the same sort of analysis. What's the functional group? It's a terminal alkyne. Do I know any carbon-carbon bond forming reactions to make a terminal alkyne? And the answer is yes. Normally you can take an alkyl halide and treat it with an alkynyl anion, and an SN2 reaction takes place, and you make a new carbon-carbon bond. But you have to also remember the properties of these reactions. Is this reaction going to give me this alkyne? You have here a strong base as well as a good nucleophile. And remember, this is a secondary alkyl halide. When you have a strong base and a secondary alkyl halide, an E2 elimination would occur. So even though this is a reasonable material to use to make this target, we just can't make it by chemistry that we know at this point. So I would dismiss this route. So immediately the 4 ways to make this target, I just will take this one out of the picture. So these hopefully will be easier. Let's start at the top. I know I can convert this alcohol to this carboxylic acid, so now I'm focusing all my attention on this. This is my new sub-target. What is it? It's an alcohol. Do I know any carbon-carbon bond forming reactions to make an alcohol? Yes, you do. You can make that bond, and that bond is made by a Grignard reaction. If I had this Grignard reagent and I treated it with formaldehyde, I would end up with this alcohol. Grignard reagents, you can only make them one way, so there really is no question about that. You can make it from this alkyl bromide. Bromocyclohexane is converted to cyclohexyl magnesium bromide upon treatment with magnesium metal. That's it. That's the only way to make the Grignard reagent. Now I think I can go forward. I have the right number of carbons, 6 carbons, that come from cyclohexanone. This carbon's in a different oxidation state. Obviously, there's a hydrogen here, there's no hydrogen here. So the question now is, what's the missing link here? What functional group can be made from the ketone and converted to the alkyl halide? So is there a functional group that can be made from a ketone and then converted to an alkyl halide? And the answer is sure there is. It's an alcohol. We know that we can reduce a carbonyl to this secondary alcohol with sodium borohydride. All right, let's continue with the other branches in the tree. How about this nitrile? This is my new sub-target. I want to focus on that. Where do nitriles come from? Well, nitriles come from SN2 reactions with cyanide on an alkyl halide. So this is a reasonable synthetic reaction. This is not very basic. You're not going to get an E2 elimination. You can do an SN2 on the secondary alkyl halide, and you get this nitrile. Well, we've already explained how to make this bromocyclohexane, so I don't have to repeat that. What about this one here, this Grignard reagent? Well, we said that a Grignard reagent is made from the alkyl bromide, and we already explained how you make the alkyl bromide in the other 2 retrosynthetic branches. So this is a complete retrosynthetic analysis on this synthetic target, where you go back a little bit, and then we even went forward. So there's a little bit of synthesis and retrosynthesis. I'm just doing this to give you an idea of how you can tackle a problem like this, and you're going to do these other two on your own, and solutions will be posted. Now, this is just the type of thinking that you should do before you actually commit yourself to a synthetic route. So in problems that you're going to be asked in your textbook and on exams, it's always going to be propose a synthesis. So you can choose any of these three feasible routes would be a reasonable answer to put down as a forward synthesis. Any one is fine. So I just randomly chose this particular route with the hydrolysis of the nitrile to the carboxylic acid. So I'll write down all of my synthetic intermediates. Right, so I said the ketone can be reduced to the alcohol is converted to the alkyl halide is then converted to the nitrile, and the nitrile is hydrolyzed to the carboxylic acid. So now I'm writing it out in the forward direction, and I have to now put in the reagents. Sodium borohydride and ethanol can be used to reduce the ketone to the alcohol. The secondary alcohol could treat it with HBr to make the bromide or PBr3. Sodium cyanide or potassium cyanide will convert the alkyl bromide to the nitrile, and then hydrolysis of the nitrile to the carboxylic acid is the last step. So on your own, solve the synthesis of compounds 2 and 3, and use an approach something like this to help you come up with reasonable forward syntheses. The functional groups you've encountered thus far that contain hydroxyl substituents are alcohols, phenols, and carboxylic acids. They each have a different pKa. Alcohols are the least acidic, and carboxylic acids are the most acidic. On this slide, we'll use the concept of charge delocalization to explain the difference in acidities of these OH groups, and also the difference in basicities of the corresponding conjugate bases. When you take the proton away from an alcohol, you end up with a localized alkoxide anion. This is a localized charge, which means that no other atoms in this molecule can share that minus charge. There are no other resonance structures you can draw that shows the minus charge localized on any other atom. Compare that to a phenol. When you take the proton away from the OH of a phenol, you end up with a phenoxide anion. And unlike the alkoxide anion, in this case the charge is delocalized because the O- is conjugated to the pi system of the benzene ring, and it's possible to draw resonance contributors that show the minus charge localized on different atoms in the ring, in this case atoms 2, 4, and 6. The major resonance contributor is the one that has the minus charge on oxygen, because oxygen is more electronegative than carbon, but the benzene ring is helping out, which means that because this charge is delocalized, it makes this phenoxide anion more stable than the alkoxide anion. Remember, the more you can delocalize a charge, the more stable it is, the easier it is to form. Compare that to a carboxylic acid, where you make the carboxylate anion where the charge is delocalized. There's only 2 resonance structures, but the minus charge spends 100% of its time on an oxygen, on atoms more electronegative than carbon, and that makes the carboxylate anion more stable than the phenoxide anion. Therefore, the order of relative stabilities for these 3 conjugate bases is carboxylate is more stable than phenoxide, and phenoxide is more stable than alkoxide, which means that the carboxylate is less reactive than a phenoxide, and the phenoxide is less reactive than the alkoxide. So the conjugate, the order of the basicity for the conjugate bases would then be the alkoxide is more basic than the phenoxide, and the phenoxide is more basic than the carboxylate. Think of, to help you understand this, think of HCl, hydrochloric acid. It's a very strong acid, pKa of 0 or below, which means that it's completely dissociated into H plus and Cl minus. That means that Cl minus is, if you will, a happy anion. It's content to exist as Cl minus. It is not looking to couple with H plus to form HCl. HCl is strong acid, very low pKa, which means that its conjugate base, chloride, is an extremely weak base. And we use that same concept here. We have the pK of a carboxylic acid is 5. It is a stronger acid than the pK than an alcohol, which has a pK of 16. Therefore, its conjugate base is going to be a weaker base than the conjugate base of an alcohol. So carboxylates are less eager to pick up a proton than the alkoxide anion, which has the localized charge. Let's use what we've discussed so far about the relative acidities of alcohols, phenols, and carboxylic acids to answer the practice problem on this page. You're asked to list under each structure below the bases, these are all the bases here, that can fully deprotonate each of these molecules, that is, shift the equilibrium far to the right. How can you approach a problem like this? Let's start with the alcohol. I'll start you off and then you can complete the problem on your own. An easy way to do this would be to take the molecule you're examining, the acid, and the base that you're treating it with. Let's take this alcohol and we'll take hydroxide. And we'll put it in the equation, the general equation that's shown at the bottom of the page, where we have an acid reacting with a base, and it forms as products the conjugate base of the acid and also the conjugate acid of the base. Let's write out the conjugate base of the alcohol and the conjugate acid of hydroxide. That would be the alkoxide anion and water. So, reaction should shift to the right if the pKa of HA is less than the pKa of HB. Let's say at least 2 pKa units. That is, HA is more acidic than HB. Equilibrium would be shifted to the right. Reaction would shift to the left if HA had a pKa that was greater than HB. That is, HB is more acidic than HA. This is basically saying that equilibrium will be shifted in the direction in which the stronger acid is giving up a proton. Doesn't that make sense? The stronger acid is more willing to give up a proton. Therefore, equilibrium will be shifted in the direction in which the stronger acid is giving up a proton. That means we have to know the pKa of the acid going in the direction from left to right and from right to left. So in this case, HA is the acid giving up a proton to form the alkoxide anion, going in the right direction. Going in the left direction, water would be giving up a proton to the alkoxide anion to form the alcohol and hydroxide. The pKa of an alcohol is about 16. The pK of water is about 16. So would you expect hydroxide to fully deprotonate every single molecule of alcohol in solution and shift equilibrium to the right? Well, no, equilibrium is shifted in neither direction because the pKa's of the acids going in each direction are pretty much the same. So at equilibrium, you would have a solution that would contain all 4 of these species. Therefore, hydroxide is not basic enough to take the proton away. Let's do one more example. Let's go to sodium amide, NaNH2. Now I've changed the base and its conjugate acid. Here we have going in the direction from left to right, NH2- taking a proton away from the alcohol, which would form the alkoxide anion and ammonia, which is the conjugate base of NH2-. Going from right to left, we would have the alkoxide anion taking a proton away from ammonia to form the alcohol and NH2-. Which is the stronger acid? Well, the alcohol is a much stronger acid than ammonia by many pKa units. Therefore, equilibrium will be shifted in the direction, greatly in the direction, completely in the direction in which the stronger acid is giving up a proton. Therefore, the answer to the question is NH2- a strong enough base to take the proton away from this alcohol, that is to fully deprotonate it, that is to shift the equilibrium completely to the right? Yes, certainly it is. So this one definitely would appear in the list of bases that would deprotonate, fully deprotonate this alcohol. What you should do then is continue with the bases that we've not discussed and answer this question, and also take a look at these other substrates, the phenol and the carboxylic acid, and find out which bases, if any, would deprotonate each of those. Solutions will be posted. Up to this point, you've encountered the following reactions of carboxylic acids. Carboxylic acids reacting with base. It could react with an anionic base to form a carboxylate and a neutral species. It could react with a neutral base like ammonia to form a carboxylate and a protonated conjugate acid of the base, in this case an ammonium ion, so you'd have ammonium carboxylate. And the other reaction you encountered was the reduction, chemical reduction of a carboxylic acid to a primary alcohol with lithium aluminum hydride. Some of the most important reactions of carboxylic acids are those which convert the carboxylic acid to its common derivatives, shown on this page. For example, acid halides, esters, amides, and anhydrides. This will be the topic of the next chapter. Nitriles are molecules that have a carbon-nitrogen triple bond. And much like carbonyls, they are a polar functional group where the electrons are polarized toward nitrogen, and the carbon attached to nitrogen is electrophilic and can be attacked by nucleophiles. One of those nucleophiles that attacks nitrile carbons is hydride. Recall that lithium aluminum hydride was a hydride source that can react with functionality in addition to aldehydes and ketones. For example, nitriles can be reduced with lithium aluminum hydride to primary amines, and note that you have two hydrides, two hydrogens from lithium aluminum hydride added to what was once the carbon of the carbon-nitrogen triple bond. And the reason that it's so is because you have two pi bonds. Hydride can add to end up making a molecule that still has a carbon-nitrogen double bond, so it's possible to have a second hydride add, and that's why you have two hydrogens attached to the carbon that was once the carbon-nitrogen triple bond. We'll encounter reduction of nitriles to form primary amines again in the chapter on amines. Even though the carbon-nitrogen triple bond of a nitrile has two pi bonds that could react with two equivalents of hydride, it's possible to stop the reaction after the addition of one hydride if you use a reagent called diisobutyl aluminum hydride, or simply dibal-H. It has one aluminum hydrogen bond, and notice it has these bulky isobutyl groups attached to aluminum. When reaction occurs between the nitrile and dibal-H, the nitrogen lone pair electrons will bond to the Lewis acid aluminum, and you end up by forming a species like this, with nitrogen having a positive charge. That makes this bond even more polarized toward nitrogen, and it makes this carbon even more reactive to nucleophilic attack. So hydride is delivered and you end up forming a species that looks like this. And you still have a carbon-nitrogen double bond. What's preventing a second hydride from attacking this carbon is the bulky isobutyl groups that are attached to aluminum. So if another molecule of diisobutyl aluminum hydride tried to approach, it would be repelled by these bulky isobutyl groups. Therefore, this sits in solution until you add water. Water will, much in the same way that you hydrolyze an oxygen-magnesium bond in a Grignard reaction, water will hydrolyze the nitrogen-aluminum bond, and you end up forming an imine. If you recall from the chapter on aldehydes and ketones, imines were formed from an aldehyde or a ketone. In this case, it would be formed, this one would be formed from an aldehyde, and it's perfectly possible to take an imine and hydrolyze it back to the original carbonyl compound. And that's what happens here in solution with this water. After the initial hydrolysis of the nitrogen-aluminum bond, the resulting imine that's afforded also is hydrolyzed, and you end up forming an aldehyde. Therefore, you can take a nitrile, and when treating it with diisobutyl aluminum hydride, you can afford the corresponding aldehyde. So a synthetic conversion of nitrile to aldehyde is possible. We saw that nitriles, like carbonyl compounds, react with hydride. Nitriles also react with Grignard reagents, and in this case, a Grignard reagent will add to the polar carbon-nitrogen triple bond. You form a new carbon-carbon bond, and you have a species that has a CN double bond. Only one equivalent of Grignard reagent will add. If a second one added, you would have too much negative charge buildup on this nitrogen. It would be almost like having a 2- charge on nitrogen. So the reaction stops after one addition of Grignard reagent, and you end up with a C double bond N. When you hydrolyze this species, you end up forming an imine, and the imine would then hydrolyze to form a carbonyl compound, just like when you had the imine-like structure formed during the dibal reduction of a nitrile. Here we have, instead of hydride being added, we have an R group being added. We still get a C double bond end, and this will form an imine, and hydrolysis will form a carbonyl. But instead of an aldehyde, now we have a ketone as a product. So it's possible to convert a nitrile to a ketone. Notice that the bond that you're making is the bond between the carbonyl and one of the R groups. Using this chemistry, let's try to synthesize dicyclopentyl ketone from cyclopentanol. We know that the bond that's being constructed using this method is the bond between the carbonyl and one of the R groups. The carbonyl portion on the left-hand side must have come from the nitrile, because this carbon, the carbonyl carbon, came from the nitrile carbon. Therefore, this portion comes from the nitrile, and then the portion on the right had to come from the Grignard reagent. Taking that into account, we would then know that I would need this nitrile and this Grignard reagent in order to make this bond. Now I have to focus on the preparation of each of these components. For example, the nitrile. How do you make a nitrile? Well, you only know one way to make a nitrile, and that is by cyanide doing an SN2 reaction on a primary or secondary alkyl halide. And the alkyl halide, in turn, could readily come from the alcohol cyclopentanol, chemistry from last semester. The Grignard reagent, well, there's only one way to make a Grignard reagent, and that's from the alkyl halide, and of course, we just said the alkyl halide can come from the alcohol. After this analysis, now I can write out the answer, the proposed synthesis. I could easily convert this alcohol to the alkyl bromide with PBr3. I could have written HBr. Either one would be a suitable reagent. In order to make the nitrile, I would have to treat the alkyl bromide with cyanide. And in order to convert the nitrile to the target, I would need the cyclopentyl magnesium bromide Grignard reagent. and the Grignard reagent would come from the alkyl halide. So you would take some of the alkyl halide, convert it to the Grignard reagent, some of the alkyl halide, and convert it to the nitrile. And then you'd treat these two with each other, and you end up with your synthetic target.